Okay, yes, there is a nice little recipe or set of procedures that they give to you for sketching. Okay, so the first step in sketching a graph is to find the domain. Okay, if we have domain restrictions, you know there are possibly holes or vertical asymptotes. Okay. Number two, you always want to reduce the function because reducing the function does tell us exactly where holes are or vertical asymptotes. So 2 and 3 are directly related to each other. 4 is going to be then finding X and Y intercepts. Those are usually very easy points to do because to find an X-intercept, all you got to do is set the equation equal to 0, and to find the Y-intercept, you set the X equal to 0. Okay, so those are usually really easy. Number 5 is your end behavior, so that's analyzing, is the function bigger on top or bigger on bottom? Where is your horizontal asymptotes? 6, I generally do not check for symmetry, personally. But you can, of course, and sometimes that'll help you draw something. And then we're going to get into 7, where we're going to find the first derivative, and we're going to find maxes and mins. And then even get into number 8, where we find concavity. So that helps us with the curvature of the graph. And then we just put it all together and hope for the best. Okay, you ready? Here we go. On my back. I feel like that's not easy to access. All right, so question number 1. The nice thing about this one is they give us an original and they've already derived it for us. So they give us a first derivative, a second derivative, so we can kind of just start peeling information off of this. Okay, so the first thing that I want to do is find the domain, and to find a domain restriction, I'm looking at the original function, and I'm looking for anything that sets the denominator equal to 0 and any kind of square roots. So is there any value that would make the denominator 0?
0.
No.
1. No, wait. There would be a negative value. No. Impossible.
It is impossible, okay? Usually when you have an x in the bottom, you do have a restriction, but because you have a squared, that turns it positive, and if you add 1 to a positive number, you're never going to get 0, right? So we do not have a domain restriction, so our domain is going to be all reals. Vertical asymptotes, how do you identify vertical asymptotes?
Cancel.
Okay, yeah. Well, canceling is the holes. Vertical asymptotes is anything that makes the denominator 0. Okay, so in this scenario, we have no vertical asymptotes. Holes is if we canceled. Did we end up canceling anything for simplification? No, so we got no holes, not a lot of information so far. The x-intercepts. Okay, so an x-intercept is if I set the equation equal to 0, if I'm working with a rational equation, that's going to be basically just setting the top equal to 0. So if I set the top equal to 0, where is my x-intercept? 0. So 0, 0. Just so you know, they like to list intercepts as points. So it's probably good to get into that habit. Set the equation equal to 0. So with a rational equation, set the top equal to 0. Okay. For the y-intercept, we're going to set the x is equal to 0. So if I set the x is equal to 0, where do we find a y-intercept? 0. Yep. All right, so end behavior, this is going to come into play for this one. So we have an end behavior, we have a rational equation. So is this one bigger on top, bigger on bottom, or same? Bigger on top. So what happens when it's a bigger on top scenario?
Horizontal.
Not horizontal.
Same.
Square.
Slant. What? Who said that? Oh, hey Jake. Should talk louder for me. Good. Slant. Okay, so we know that this function is either going to be a positive slant like this, or it could be a negative slant like this. Okay, so how am I going to decide which it is? So I want to say as x approaches positive infinity, what is going to happen to my y value? Okay, so kind of like if I plug a positive infinity into that equation, it's going to be a positive over a positive, so it's going to go to positive infinity. So then I can say, oh, well then, as x approaches negative infinity, usually it's going to go to negative infinity, but not always. It's possible to have a slant that looks parabolic, so you should always double check and plug negative infinity into the original. So if you were to plug a negative infinity in, you'd get a negative on the top, positive on the bottom, and so we do know that the y does in fact go to negative infinity. Okay, so we have this some kind of like slanty thing going on. Okay, we can check for symmetry. Do you guys remember how to check for symmetry? Yeah, so if you pick a number, like let's say we pick 1 and we plug it in, and then we get, I don't know, let's say we get 5, and then we are going to plug in -1. So if we get 5, then it's symmetrical over the origin, like a parabola. But if we get -5, then it's symmetrical over the origin. So that's like kind of like a John Travolta. Okay, so if we plug 1 in, we would get 2 over 2, which is 1. Okay, so if I plug 1 in, I get 1 out. So now let's test it with a negative. If I plug -1 in, what do I get out? -2. So what do I know? Symmetrical over the origin. Good. Okay. All right, so now we have to identify where the max and the mins are. So what piece do I use for that? First derivative, good. So I need to take that first derivative and set it equal to 0. So I don't know if I need to do that algebraically, or can you just do that mentally? If I set that equal to 0, we want to consider the bottom ever equaling 0. Is it possible for the bottom of that second derivative to equal 0? Positive number squared is just always going to be a positive number. On the top, if I set each of those two quantities equal to 0, where do you find the maxes? At 0, and the x squared plus 3 is a square, well, square root of -3. So therefore is an imaginary value. So the only max value we get is 0, but, okay, never mind. So 0, so if I plug 0 in to my original function, what is my corresponding y value? Oh, hold on. My bad. This is my critical number. 0 is my critical number. So I have to do a number line test to decide if it is a min or max. Okay. So if I plug a value less than 0 in
-1
to my first derivative, like -1, so remember this is a first derivative test, so if I plug -1 in, I would get a positive, good. And what happens if I plug +1 in? You get a positive again. So this function goes up. So what is happening potentially at 0? It's not a min because it's not, it goes up and then it goes up again.
It's a sharp turn.
It could be a sharp turn. It could be a point of inflection, right? Good. Inflection, yeah. So we do not have a max or a min. Okay, but to find the point of inflection and verify that it is in fact, or potentially could be some kind of something, we take the second derivative, so point of inflection, second derivative, and if I set that equal to 0, I can get critical values at, yeah, 0, and this one does pop out, wow, I can't even draw a minus, plus or minus the square root of 3. Okay, so I'm going to do a second number line test, but this time using the second derivative, and this is going to reference my concavity. So I got a negative square root of 3, 0, and a positive square root of 3. Okay, so if I was going to plug in a value less than the square root of 3, such as like negative 2, okay, negative 2. So if I plug in negative 2 down here, so negative 2 into this, I would get positive over a positive. So that little piece would be positive. Okay, if I plug a value between negative the square root of 3 and 0, such as negative 1, so if I plug in negative 1, I get positive. If I plug in negative 1, I would get 1 squared minus 3, so this piece would be a negative. So my top would be negative, bottom is positive. So I get a negative, yeah. Okay, if I plug 1 in, positive 1, I would get negative times a negative, so the top would be positive over my positive. So I get a positive. And then if I plug in, let's say, what did we use before, 2? 2 again. Okay, so this would be a negative. That would turn into a positive, so my top is negative over the positive. So what can we conclude from this? Yeah, we have 3 points of inflections, right? Okay, so we have a point of inflection at a negative square root of 3. So if I plug a square root of 3 in to my original, I would get out, I'll just tell you what you get. You get negative 3 square root of 3 over 2.
What?
Because 3 square root of 2 over 2. Sorry, I said that wrong. So because if I plug in a square root of 3, the square root of 3 squared is 3, and then you still have the square root of 3. So you have a 3 times 2 on the top, which is 6 square roots of 3. Then on the bottom you get 3 plus 3, which is 4. So 6 fourths reduced to 3 halves. So there's that one. We also have a point of inflection at 0, 0, which we've talked a lot about. And then a positive square root of 3 will result in a positive 3 square root of 2 over 3. Over 2. I can't read. But I wrote it right, so it's important that you can also... My hand is now fixed and my mouth is broken. It's all good. We got it. Okay, so I'm going to graph all of the stuff that I have. Okay, so I have 0, 0. I have the square root of 3 and a negative square root of 3 and negative. So I think that's like just slightly below negative 2. And then the other one is going to be right about here. So those are my 3 points. Okay, so remember that this function is continuous. And basically all we're going to do is kind of connect the dots with correct curvature. Okay, so if I start to the left of this negative square root of 3, okay, so I know that the end behavior has to be going down to negative infinity, right? Okay, I also know what kind of slope does it have. A positive slope. So I know it has a positive slope, and I also know it has what kind of concavity. Positive, right? So if I kind of connect my hands for the happy face, okay, one of them has a positive slope. Which one has the positive slope? Yeah. So I'm just going to kind of draw that curve right there. Okay, so it's going to kind of have this like cup shaped. So it's still going down, but it does seem to kind of level a little bit. Okay, so now I need to get from these 2 points. Okay, so between a negative square root of 3 and 0, what kind of slope do we have? Positive. Okay, and then between the square root of 3 and 0, the concavity we have is negative. So we have a sad face with a positive slope. So which one has a positive slope? This one, right? So I'm going to draw that cup between those 2 points. So it's going to kind of cup with a sad face. Whoa. Okay, and then I'm going to connect the next 2 points doing the same thing. Okay, so now I have, when it's greater than 0, I still have a positive slope. And greater than 0 and square root of 3, we have a happy face. So which one am I going to draw that has the positive slope? This one, right? So now we're going to have that lower cup there. Okay. Okay, and then the last one, positive slope, sad face. Okay, so now we're going to put that curved up. Yeah, it's like an ultra John. That's actually kind of hard to say. Okay, how'd you do with that one? Did that make sense with the the 2 sides of the sad face or the happy face with the slope thing?
So the critical number is the first derivative is the slope and then the second is the happy.
Right. Yep. All right, let's try another one. I think there's 3 of these that we have to do. I think so. 3. All right. Okay, so question number 2. The first thing I see on the bottom is that can we factor that bottom of the original function? Are there 2 numbers that multiply to 1 and add to negative 2? Because I really like factored form. So x minus 1 squared, right? Okay, and I like that because that's way easier to work with, especially when I'm trying to find domain restrictions. Okay, what value is going to make that denominator 0? 1. So the domain is that x cannot be 1. And what is happening? Does that 1 cancel with the top? No. So that means there's not a hole, there's a vertical asymptote. So we have a vertical asymptote at x equals 1, but we have no holes, there was no canceling. Okay, for the x-intercepts, what do I do? Okay, yep, we just set the top equal to 0. We get 2/3, so we would say 2/3 and 0 as the point. Wow, that was a bad 0. Okay, my y-intercept, I'm going to set the x equal to 0. So if I set the x equal to 0, I get negative 2. Good. Okay, and behavior, I can go back to the original form and think, is it bigger on top or is it bigger on bottom? Bigger on bottom, so where's your horizontal asymptote? Good. So we can say horizontal asymptote at y equals 0. So you can write it as a horizontal asymptote, or you can write it as x approaches infinity, the y goes to 0, and as x approaches negative infinity, the y goes to 0. Symmetry. Okay, so for symmetry, I'm going to pick a value such as 1 and see what I get, and then we'll plug negative 1 in. So if I plug 1 in, I'd get 1 on the top. Oh, okay, so 1 was a bad choice. Never mind. Don't pick 1 because 1 is an undefined value. How about 2? So if I plug 2 in, 6 minus 2 is 4 on the top, 1 on the bottom, I get 4, right? 4. Okay, and if I plug negative 2 in, I'd get negative 6 minus 2, which is negative 8. And on the bottom, I'd get negative 3 squared. Yeah, not 4, right? Not 4. Not 4 or negative 4. So this function has no symmetry. Okay. So for relative mins and maxes, set the first derivative to 0. We got to find our critical number. So first derivative, remember you have to have your domain restrictions as critical values. So 1 is one of your critical values. Also, if we set the top equal to 0, we also get 1 at 1/3. Good. Okay, so I'm going to do a first derivative number line test with 1/3 and 1. Okay, and I do know that 1 is a vertical asymptote. I don't know why I like to draw like a pretend vertical asymptote on the number line, so I just remember that. So if I plug a value less than 1/3 in, such as 0 into my first derivative, I would get a negative, yes. Okay. If I plug a value between 1/3 and 1, such as 1/2, okay, 1/2, so negative 1.5 plus 1 is a negative on the top, a negative on the bottom, so we get a plus. Okay, and if I plug 2 in, we're going to get a negative on the top, positive on the bottom, so we get a negative. So this function goes down, up, down. Okay, so remember that 1 is a vertical asymptote, so what did we just find out? It's not continuous, and do we have a critical, or do we have a max or min? We have a min. Okay, we have a min at the x value of 1/3. So we have a min at 1/3, and if you plug 1/3 into your original function, I'm just going to tell you that you get negative 1/4, or negative 9/4, wow, out. We do not have a max. Okay, and then the last piece now is using our point of inflection information. So I'm now working with the second derivative. So again, my critical values, I want to list my 1 again, because it makes my function undefined. And if I set the top equal to 0, I have 0. Okay, so I'm doing a number line on the second derivative. We can use 0 and 1. Remember, 1 is a vertical asymptote. Okay, so plugging this into the second derivative, a value less than 0, such as negative 1. So we get a negative over a positive. So negative. If we plug in a positive, let's say 1/2, we get a positive over a positive. And if we plug in 2, we get a positive over a positive. So, did we find a point of inflection? We're at 0. Good. And if I plug 0 into the original equation, I get negative 2. Good. All right, so I'm just going to draw the information as I go down. Okay, so I have a vertical asymptote at 1. Okay, I have an x-intercept at 2/3. I have a y-intercept at negative 2. I have a horizontal asymptote at 0. I have a relative minimum at the point 1/3, negative 9/4. So that's below negative 2, by the way. So that's like, shoot, right there. And then we also have, did I list everything? Yeah, okay, that's good. Okay, so I always like to go left to right. So because I have a horizontal asymptote, I know that the function is going to exist on one of these two sides and infinitely hug this. Okay, and because I have some points below, I know that this little slide is going to kind of come below. Okay, so I know I'm going to have this downward effect. It's going to come and cross at 2. Okay, what's going to happen at this point right here? Well, it's a minimum, right? So it's minimum. So I know it's going to come down, cross through, bounce back up, and then I'm going to cross through the x value of, what was that? 2/3. Okay? So remember that, like, stuff we did before with, like, asymptotes and how many times it crosses, if it crosses or if it bounces? Okay, this one I really don't need the concavity to help you figure it out. Okay, the concavity really just gave me an additional point, but I kind of had that. Okay, so now my right side of this is either going to be a slide on this side or above the horizontal asymptote or below. So you can use the idea of a vertical asymptote. What kind of vertical asymptote do we have? Is it an even one like a volcano, or an odd one where it splits? Even. So I know that they both go up, so this side is going to come from up as well, and then curve down towards it. And we can verify that too with our first derivative. We know have a negative slope. So if I drew this, would that have a negative slope? And would it have a happy face?
Yes.
Yeah. Okay, we really don't have any other information. I could plug in more points for that slide to be more accurate, but that's the only way you could really become more accurate. All right, last one. All right, ooh. Look at that domain restriction right off the bat, huh? So a domain restriction is going to come from 0 in the bottom or a square root. Okay, so you can't take the square root of a negative number. So the inside of the square root is x squared plus 2. Will x squared plus 2 ever equal 0 or ever be negative? No. So do I have a domain restriction? No. So this one actually has no domain restrictions, even though it looks like it really should. Does it have a vertical asymptote? Is there any value that makes the denominator 0?
No.
No. No vertical asymptote? Anything that cancels to create a hole?
No.
No. Okay. An x-intercept, if I set the top equal to 0. 0, 0. They're all not no. Okay, so my y-intercept, if I plug 0 into the x, you get 0 again. Okay, end behavior. What about the end behavior? Do you guys remember this situation? If I have a square root? So do you remember that if I take the square root of the bottom piece, the square root of x squared is plus or minus x. So I have a same case scenario. So where's my horizontal asymptote? At -1 and +1. So I have one at -1 and +1. So we have horizontal asymptotes at y equals plus or minus 1. So this one might be helpful for us to figure out as x goes to positive infinity, is it going to the +1 or is it going to the -1?
It goes to.
Okay. Yeah, so like when you simplify, it's like the plus or minus makes for a potential negative. So as x approaches positive infinity, let's see which one it's going to. So if I was going to plug a positive in infinity, would I get a positive or a negative number? Positive. So that means it's going to +1. Right? So if I plugged in the negative, x goes to negative infinity, that one's going to go to -1. So 2 asymptotes. This will be interesting. We can check symmetry. So let's say we pick 1. If I plug 1 in, I would get 1 over the square root of 3. And if you plug -1 in, you get -1. So you get the negative version, so therefore it's symmetrical over the origin. Okay. For the relative max, if I set the second derivative equal to 0, top isn't going to equal 0, bottom isn't going to equal to 0, no critical values. No critical values. So no max, no min. Okay, what about the second derivative? If I set the top equal to 0, ooh, we finally got some information. We get 0, and if I set the bottom equal to 0, I get nothing. So 0 is my only critical value on my second derivative. If I do a second derivative number line test, plug a value less than 0 in, such as -1, I would get a positive. If I plug a value greater than 0 in, I would get a negative. There we go. So we have a point of inflection at the point, our one and only point, 0, 0. All right, so we know it crosses at the point 0, 0, and we know that there's a horizontal asymptote at 1 and one at -1. So, can anybody envision what is happening? Yeah, sideways John Travolta, that is basically existing in between those two asymptotes. Okay, so it always is increasing in slope, but you have a happy face on the left and a sad face on the right. Good. Okay, that's all I got for you guys.
Yeah.